Imagine navigating the world without relying on sight the way we do, without ears tuned for complex sounds, and without a strong sense of smell through your nose, and yet still being able to track prey, avoid danger, and find a mate with incredible precision. Snakes live in that world. They glide across forest floors, deserts, and oceans, constantly flicking their tongues as if they're tasting the air. It looks simple, almost strange, but it's actually one of the most refined sensory systems in the animal kingdom. So how do snakes smell without noses? Let's break down what's really happening inside that flicking tongue and hidden sensory organ, and uncover how snakes interpret the chemical world around them. Right here, on History of Simple Things. When we think about smell, we picture air entering our nostrils and odor molecules binding to receptors inside our nasal cavity. Snakes do have nostrils and a standard olfactory system connected to their nasal passages, and they use it for basic airborne smells. However, that system plays a secondary role compared to something far more specialized. The behavior most people notice, the constant tongue flicking, is central to how snakes truly detect scents. Their tongues are forked, splitting into two flexible tips. Each flick collects microscopic chemical particles from the air or ground. Instead of analyzing those particles in the nose, the snake retracts its tongue and inserts the tips into small openings in the roof of its mouth. This is where the real chemical detection takes place, using a structure specifically adapted for interpreting environmental signals. That structure is called the vomeronasal organ, also known as Jacobson's organ. It sits on the roof of the mouth and consists of two fluid-filled sacs lined with specialized receptor cells. When the tongue delivers chemical particles into the organ, those molecules bind to receptors that trigger nerve signals to the brain. Unlike general smell receptors in the nasal cavity, the vomeronasal organ is particularly tuned to detect heavier, non-volatile chemical compounds, the kinds that stick to surfaces or linger in the air at low levels. This makes it extremely effective for tracking scent trails. The forked shape of the tongue plays a critical role here. Because each tip gathers particles from slightly different positions, the snake can compare input from the left and right sides, allowing it to determine the direction of a scent source with surprising accuracy. This directional sensing is one of the most impressive aspects of the system. As a snake moves forward, it flicks its tongue repeatedly, sampling different points in space. If more chemical cues are detected on one side of the tongue than the other, the brain processes that imbalance and adjusts the snake's movement accordingly. In this way, a snake can follow the invisible trail left behind by prey, even if the animal has already passed by minutes earlier. This form of chemoreception helps snakes hunt rodents, amphibians, birds, and other prey species, depending on their habitat. It also allows them to detect predators and recognize pheromones released by potential mates during breeding season. Rather than experiencing smell as a broad, blended sensation like humans do, snakes build a layered chemical map of their surroundings. Different species rely on this system in slightly different ways, depending on their ecological niche. Pit vipers, including rattlesnakes and copperheads, combine chemical sensing with specialized heat-detecting pit organs located between the eye and nostril. The heat pits detect infrared radiation from warm-blooded animals, while the vomeronasal system confirms chemical identity. Together, these systems create a detailed sensory profile of potential prey. Sea snakes adapt the same tongue-flicking mechanism to aquatic environments, sampling chemicals dissolved in water rather than airborne particles. Burrowing snakes use it to detect scents trapped in soil or under leaf litter. Across habitats, desert, forest, grassland, or ocean, the fundamental mechanism remains consistent. The evolutionary development of this system is shared across many reptiles, though it is especially refined in snakes. Lizards, for example, also possess a vomeronasal organ and engage in tongue flicking, but snakes appear to rely on it more heavily. Over millions of years, as snakes evolved elongated bodies and lost their limbs, other senses became increasingly important for survival. Chemical detection offered a reliable way to gather information without needing complex facial expressions, grasping appendages, or high visual acuity. The neural pathways connecting the vomeronasal organ to the brain are well developed, allowing snakes to distinguish specific chemical signatures associated with prey species or individuals of their own kind. This precision gives them an advantage in environments where visual cues are limited. It's important to clarify that snakes are not smelling with their tongues in the literal sense. The tongue itself has no smell receptors. It acts purely as a delivery tool, transferring environmental chemicals to the vomeronasal organ. Meanwhile, the standard olfactory system in the nasal cavity still functions during breathing, contributing to general odor detection. However, for most species, the vomeronasal system provides more detailed and behaviorally significant information. The frequent tongue flicking isn't random or decorative. It is continuous sampling, allowing the snake to update its chemical map in real time. The coordination between tongue, vomeronasal organ, and brain forms an integrated sensory network that compensates for limitations in other senses and supports survival in diverse environments. So while snakes do have noses, their primary method of detecting scents relies on a far more specialized system hidden inside the mouth. By flicking a forked tongue and delivering collected particles to the vomeronasal organ, they interpret chemical signals with remarkable precision. This adaptation allows them to track prey, sense predators, and navigate complex environments without relying heavily on traditional nasal smell. What looks like a simple tongue movement is actually a sophisticated biological process shaped by millions of years of evolution. Understanding how snakes perceive the world reminds us that smell, like all senses, can take many forms, and sometimes the most effective solutions are the ones we least expect. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.